Welcome back. So let's get right into it, shall we? JCM-1 has seen a lot of changes since we looked at it last. Last time you saw it, I had it built on these breadboardy things, but ran into a lot of problems with that, particularly with ground balance, noise interference, loose connections, and a whole bunch of other crap. So, we just decided to go ahead and graduate to wire wrap. A lot of help from Garth Wilson on that. Not insofar as his website has a lot of information on that. I'll link that in the description. The guy is basically a 6502 genius. So if you're doing anything with 6502 bus-based computers, look him up. The guy knows basically all there is to know about that. So let's take a look at this. I'll change to wire wrap. The layout and design isn't significantly different from before, and really the schematic is pretty much the same as it was. No huge changes there, and it's just basically on wire wrap instead of breadboard. As far as wire wrap goes, keep an eye out. I'll be doing a really quick wire wrap tutorial of the things I learned while I was learning how to do wire wrap. Just for interest purpose, I guess. I don't know. So look out for that one. First thing I wanted to show, though, on the change here was the hex display. Yeah, remember last time we saw the hex display? It was built in, good old breadboard fashion. Well, I decided to go ahead and wire that up. Wired it up on, one of these boards, and, I got a little project I'm working on this. That's part of this. Any guesses? We'll find out later. So the hexadecimal output, I decided to name it Super Hex. I don't know why, it just came to mind. Missing a few ROM chips. I decided not to go ahead and buy those because, Super Hex isn't going to be around for too much longer. But I did decide to go ahead and put it on the board like this just to clean up its signals and make it more reliable, so I wasn't attaching a breadboard-based thing to the nice wire wrap circuit. So let's just flip it over, take a look at it real quick. That's the other cool thing about wire wrap here is I can just do this while it's on. It's like, I don't care. So yeah, this guy here, I decided to do this just with solder tail wires. Just quick and clean. I didn't want to waste all my nice wire wrap posts to do this, so I just kind of knocked that together real quick. Means that this is kind of a permanent circuit now, but I don't know, I'll frame it and stick it up on the wall or something. It'll be a memory of the design of the computer. So flip it back over and let's look at the machine proper. So this is the computer. Let's go through, some of the changes in the major details here. First is the power bus. I decided to run a power bus right down the middle of the machine, basically so that I have easy tie points right down the center to all of the chips I'm going to populate on the board. Just basically, so it's, I'm getting as close to having a ground plane as I possibly can. All my leads are short, and I don't have a lot of these power buses all over the place, adding reflection and induction and noise, acting as antennas, doing wacky stuff like that. So that's why I ran one major plane down the bottom. Lots of decoupling capacitors in here. I have like 1 nano, 1 nanos, 100 nanos, 22 nano, and like a 2.2 microfarad capacitor on that. That's for decoupling and bypassing. And I've talked about that before. You can look that up if you're interested in as to why exactly that's done. Basically, when the chips do their switching, they draw power. This helps even out the bus so you don't have lots of spikes on the power rails. The rest of the top of this, like I said, is pretty much straightforward, but let's go through everything. Reset switch. I have a whole bunch of these switches because they were really cheap. They have built-in lights, and I usually don't use the LED on it, but I decided to go ahead and wire that up so it'll act like a power light so I know when the machine's on. Especially when Super Hex gets removed, I will have no other indication the machine is running. Other than that power light. So just like an idiot-proof indicator to help me know. It's like the trouble light. Hey, check engine. Yeah, the engine's still there. This is the reset circuit. Again, schematic the same. The 555 timer, the inverter, and the timing capacitor there. You hit that. That makes a pulse. That inverts it. That sends it to the reset pin on the 6502 and to this other chip down here, which we'll get to in a second. Standard oscillator, that's the same 1 megahertz oscillator we saw before. And one thing that's missing from here, but I did accommodate, was the slow oscillator. We're getting to the point now in the design where things are pretty stable, and I don't have to have that slow oscillator to watch what the bus up here is doing to get an idea of how the machine is operating. It's pretty, how can I put it, predictable now. So I don't need that as much, but I still have it in there. And so what I do is I have a switch here that can switch this, the signal output this out to this wire wrap pin. And that means, can you guys see that? Yeah, to this wire wrap pin here. And with that wire wrap pin, I can then pull in my slow oscillator. So this is basically the same slow oscillator circuit as before, and I can I can move this wire and change whether it's running at 145 hertz or 1 hertz. And then it comes out here. I have a hand-wrapped, big, fat inductor on a metal core, on a ferrite core I made, just to even out some of that signal and noise without having to do anything wacky. Basically, I can pop that in there and slow the machine down if I want to. I also have one of these little function generator kits based on the XR2206 chip that can put out a square sine triangle. You know, if I want to play around with different frequencies for diagnostics to see, okay, this chip works at this frequency, but once I get above this other one, it screws up. I can bring in my my square output, which is the red one here. I can bring the square output into that pin and dial my dials until the machine breaks, and then I can use that for diagnostic information. Luckily, I haven't had to do that too much, but, you know, it is what it is. One thing I've noticed with Super Hex, I haven't been able to figure out yet, it's hard for you to see, but this one segment of this LED, no matter what I do, I can't get that to stay lit all the time. It does weird things. I don't know. I've resoldered it a billion times. Still can't get it to work. That's why wire wrap superior. It pretty much just works all the time. Back to other details. Let's go through the rest of the chips. Good old 6502. This is actually 65CO2 14 megahertz by Western Design Center, WDC. Decided to use that because if I ever want to speed it up down the road, I can. And the things are new and reliable, so there we go. This is our RAM chip. This is a 128 kilobyte RAM chip. And, you know, the 6502 can only address 64, but I went with this because it was basically the least expensive single parallel RAM chip I could get. That was a static RAM that I could get that would work with the 6502. I could have gone with, I had like options when I was looking of like 32s and 128s. And if I had two 32s, I'd need 2 of them, and the address bus wiring would be more complicated. You got more sockets to deal with. And we're only using half the RAM on that, but it makes it so much easier to deal with. I just tie that. I can tie that extra bit, that bit 16, either high or low, pick either half of the RAM and then just wire the rest of the thing straight to the bus, and it just works, so I don't have to worry about it. This also gives me options later. If I design for a larger RAM, I can design for things like bank switching later without having to do a lot of work with this. All I have to do is just play around with that top memory bit and basically toggle it on and off for insanely simple bank switching. You know, of course, that's going to throw our stack and our zero page, you know, awry because those Area 6502 needs. But we can do some other magic like mapping zero page and stack out to its own little small memory that never changes. I don't know. Lots of cool things we can do in the future. We're nowhere near playing with that yet. ROM chip. This is the same ROM chips as up here. I've talked about this too. Again, 128 kilobyte ROM. Exact same reason on this guy is that it was really inexpensive. It was a good single chip solution. And I didn't have to worry about trying to wire up multiple chips and all of that stuff. I could have gone with smaller ROM chips, but again, I designed this for ease of use. I can basically wire this to pins, straight to pins 0 through 15, tie 16 high or low. Either way, I don't care. I have it tied low right now. And then that means I can code my ROM for the target memory space I want in my assembler, and I don't have to worry about calculating offsets or anything like that. Also, the wiring on that makes that super simple. I just wire it straight up to the bus, and I make sure that my address decoder only enables it when we're needing to access something from the actual ROM space. Again, that also leaves flexibility. We can do paging in and out whole chunks of ROM if we want to do in ROM programs. If we want to, I don't know, throw some built-in games on the machine later that you just, you type a command and it goes boonk and it maps that part of ROM in. There's lots of extra goodies we can do that. So again, I left that in place. This stuff right here is pretty much the same. It's much more simplified from my previous version of this. I just cleaned it up a lot and removed a lot of the unnecessary circuitry. But basically, this is my address decoder. We've got two 74LS138s. Those are 3 to 8 line decoders. It takes basically a 3-bit input and gives you 8 outputs based on the binary value that it receives effectively. So if it receives a binary value of 8, which is 111, the 8th output line on that will be driven low. What that allows me to do is I can latch those into the specific parts of the address bus and decode certain things. So for example, this guy is latched into effectively the top half of the top nibble, or top byte or whatever you want to call it. That's a nibble. That's 4 bits of the address here, and decodes whether we're in ROM, RAM, or in our I/O space. And so then it comes out to one of these other 2 chips here. Let me actually look at my schematic because I do not remember exactly. Yeah. So it brings out the values E and F, the 7th and 8th output. It brings it into the 74LS08, which is I believe an AND circuit, which says that it doesn't matter if either one of those is 0, drive that output to 0. So that means no matter what, if you're in E or F in the memory space up here, the ROM will be selected. Those then come out with a combination of this value being D off of the top chip here into the 00, which is a NAND gate. Basically, that allows me to select the memory. So what it's doing is the option out of here that selects D selects I/O. So what I can do is if it's not I/O and not ROM, it must be RAM. So that's what I do with those. I tie both of those through the NAND gate, so that if it's not D, E, or F, basically, the RAM gets selected. Selecting the I/O is really simple. The I/O has one value up on the top end of the address bus here. That's value D. So the output from this chip that is D just goes straight to the I/O select line. That's so chips in the I/O space will know, okay, at least I'm in the I/O space, and the other chips are disconnected. This second LS138 decodes the I/O space itself, and it's decoding the lower 3 bits of this nibble right here. So it decodes 0 through 7 effectively. And that gives me 7 independent chunks of space that I can individually address to 7 physical devices. So that's what that's doing basically. It just got 7 outputs that I can use as chip selects for individual chips within the I/O space. Now the big thing that's different now is this chip right here. This is a 6551. This is called the ACIA. It's basically a serial chip, a serial communications chip, and I have it right now mapped into D0, the D0 space. And so when it's in when the computer's in the D0 space, if it's reading or writing from the D0 space, this chip gets selected. And it has control of the bus basically. So ROM's out of the way, RAM's out of the way, it's got control of that. This is your standard 6551 though, nothing fancy. Interesting little piece of errata on this 6551 that I'll get to in a second. I did want to come back to this guy right here, ZIF socket. This is a really wacky arrangement. I don't know if I can get this on camera there. But basically, how I have this connected in here is I've got my wire wrap pins. Then I've got a wipe socket in here because the pins of the ZIF socket would not fit into the wire wrap socket. And then I've got the ZIF socket plugged into that, so it's all sandwiched together. And of course, the reason for that is so that I can pull this chip in and out, reprogram it, play around with prototype ROMs, do whatever I want to with that chip. And I'm not trying to pry the chip out with, with the black stick or whatever, trying to get it out of there. Let's flip the machine over real quick and take a look at the back. At the wire wrap goodness, it is just a rainbow smorgasbord. I got this this 8-color wire wrap wire. It's like, gosh, it's something like a kilometer of wire. It's like over 1,000 feet of wire, or 1,000 meters of wire on this little spool. 30 gauge Kynar wire, solid, of course, designed for wire wrapping. But I got it in multiple colors so that individual functions on the machine can be wrapped with individual colors to make it a little bit easier to trace out what's going on in here when I'm playing around and diagnosing. Excuse me. I don't stick too much to any individual color pattern. I do have some pattern or some standards, like blue is my address bus and green is data. The purple wires are the outputs of the address decoder. Orange here, this main orange bus, that's our clock. The yellow here is like a reset pin. Yellow tends to be my color for generic. Don't have any other reason or any other purpose for the wire type of things. Red and black, positive, negative, obviously. I was reserving brown here, which is really hard to see on this because, it's brown on copper. But brown is for outputs leaving the machine. But as you can see here, though, I've got some just random yellow and green wires in here, and this orange one here, specifically for dealing with internal functions of the address decoder. Again, if I have to get in here and figure it out, I can see which parts of what piece of the address decoder are tied together and suss that out pretty easily visually without having to screw around with tracing wires with the oscilloscope or anything funky like that. Of course, you can see I've got decoupling capacitors in here on some of these chips. As I was building this, I kind of changed my mind on where I wanted these decoupling capacitors. Some of the decoupling capacitors are actually, you can actually see one right here. I soldered it onto the socket on the underneath of the chip, and other ones are just on the back end of the board. It just randomly where I decided to shove them. So that is the layout and everything. So let's talk about the big change that brought all this about. I was trying to add the next feature to the JCM-1 computer, and that was serial output. I wanted to be able to work with the computer and say, I don't know, program into this ROM a basic, how can I put it, a basic monitor program so that I could use my serial port to use tools on a modern computer, or even just type it right in, to program the machine in memory so I can just do on-the-fly quick testing without lots of having to reprogram ROM chips. I can just throw ideas at it, see what happens, get an idea, feel for how the thing behaves in certain things without having to write it in an assembler and assemble it and burn it to the ROM and stick the ROM and test it and take the ROM out. If I have the serial port, I can just program a quick monitor program in here, poke and peek to use the basic things, write and read any register value, any flip-flop, any input-output I want, and just to see instantly what the machine was doing. So that's why I wanted to put the serial chip in there. But I ran into a big snag with this that I thought had to do with breadboards. And this is where some help from Mr. Wilson came in, and from the folks on the 6502 group on Facebook. They're like, dude, you can't build a 1 megahertz machine on breadboards. You can't freaking do it. It's dumb. Build it on wire wrap. So I went ahead and built it on wire wrap. And I continued to have problems here. So I'm like, there's got to be something weird going on with this chip. So then I just started playing around. Again, remember, I'm trying to build this without any fancy diagnostic tools. I do not have a logic analyzer. I do not have an oscilloscope. I'm doing this, to quote Scotty, by feel of the deck plates. I'm just kind of sussing it out. And I noticed, when I was doing my earlier diagnostics, that it was fine on a slow oscillator. But when I used a fast oscillator or the built-in crystal can, it wouldn't work. I would get garbage out the other end. I wouldn't get anything out of the computer that was worth of anything. So that's where this came in as a really valuable diagnostic tool. I was able to move move this pin up and down, and tune the frequency until I got it to break. I was able to get the machine to work up to a specific speed, which was something like 40 kilohertz. It was insanely slow, by 6502 standards. And then it would just fall over. And I'm like, maybe my chip's bad? So I put a different chip in there and I got the same result. So I did Googling and Googling and Googling and more Googling. And it took me about 30 minutes to find it. But basically the problem wasn't my chip, it wasn't the computer or anything. The problem was, and if I can find it here, if I can find where I shoved it, I don't know where I put it right now, but the problem was the actual 655 ones that I was using. I ordered a couple of Western Design Center 65C51s that have a known problem where the transmit buffer empty bug is stuck on. So that means, basically the way that my program is working, in order to communicate out the port, it won't try to send another byte until it's sure that the buffer's empty. And that's a standard programming paradigm for the 6551. That way you don't lose bytes in the buffer. But it was always telling me the buffer was empty. Always. All the time. So as I sped this up, the computer ended up being faster than what the serial speed I had it set to could spit the byte out. So it started overwriting the buffer with junk, to the point to where when it was done, it was overwriting the buffer with the very last byte every single time, and all I ever got was that last byte. So what we did on that is I took those chips and I launched them out of a cannon into the sun. Not literally, but I had to get my obligatory Futurama reference in there. I took a old school 6551 out of an old Apple Super Serial card. Took that chip out of there, put it in there, and lo and behold, at 1 megahertz, the thing gosh darn works. It works perfectly fine. How's that for old technology? This has a date code of the 30th week of 1984, and it kicks that new chip's butt. Old technology is friggin' awesome. So that's basically what led me to all of this, is that wackiness on that thing. But I digress. So the 6551 is the biggest addition here. It's the ACIA chip. It allows us to do serial communication. You can look up the data sheets on the details on that, but basically it sends data out at specific baud rates that are set by what this reference oscillator, usually 1.84 megahertz or so, and then has an internal divider that gives you your different baud rates. However, this is a logic level chip. This is TTL 5-volt logic. This is not compatible directly with RS-232, which is the communications protocol. As you can see, I have it connected there. It's not compatible with that at a voltage level. It needs to be like above 9 volts or something like that for that to work. And also, if you pull 9-volt signals off of your serial line coming from your other device right into this chip, it's going to be a little grumpy with that. It's not going to like those voltages. So we put in between there basically a bus driver, a bus transceiver chip. This is the Maxim Max 233. It's effectively identical to Max 232, except this has the built-in charge pump capacitors. Now, I'll talk about that real quick. The Max 232 is the chip that most people use. In the older days, that you would use two separate chips, two Motorola chips that would effectively provide the same function. One would be two transceivers, and one would be two transmitters, and one would be two receivers or something to that effect. But then, Maxim came out with their single chip that did it, and didn't require any extra voltages. Those Motorola ones, you had to have an extra 12 volts on your board to power those chips. But the Maxim here does not require that. The Max 233 and 232s do not require that extra 12 volts, which will simplify the making of this machine. I only need to have a single 5-volt rail and it works. And that was one of my, my design goals, to keep things super simple. The Max 232 requires those little charge pump capacitors to bring the voltage, to give it oomph, to bring the voltage of those signals up. The 233 has those built in. Now, I can very easily have designed this with the 232, and in retrospect, it would have been cheaper, but you know me, I like to go for easy, so I went with just the single chip in there. This chip costs about 4 times as much as the components of a Max 232 and the capacitors combined. In future revisions of this, I might change that, if I spin a final actual PCB of this, maybe I'll sell them, I don't know. But if I finalize that, I'm probably going to change it back to the Max 232 just to cut the cost of the board down by $3 or $4. But again, I digress. So, that does that transceivery stuff on there to convert that signal over. So yeah, that's the basic rundown of that. We've got the machine up and running, perfectly stable. This is the most stable this thing has ever been. I mean, I can just, it does not care what I do to it. It's just like, okay, we're happy. It's up and stable, and it friggin' works. So let's show you what it does. For that, we need to switch over to the side cam and my side workstation. Side cam, how you doing? So let's turn on my video capture here so you guys can see what I'm doing. Okie dokie. So there is the output of the computer. It's pretty straightforward. I'm going to go ahead and clear that out. So what happens when this computer boots up? I'm going to hit the reset button. Bling! We get hello world. It says hello. If I give it any input, doesn't matter what the input is, it says hello world to me. That's basically all it does. I wanted to ensure that I had serial communications working correctly on the machine, and worked up a really quick ROM to do that. There's really nothing to that at all. I will mention this program I'm using. It's called RealTerm Serial Capture Program. This is like the hacker's serial terminal. You can diagnose all different types of serial communications. You can see over here what the pins are doing and all of that stuff. This was really helpful and helped me diagnose problems I was having with the 65C51 and determining that it wasn't wiring or anything I was doing. It was the friggin' chip being stupid. So highly recommend this program if you're doing anything with serial, if you don't already know about it. So let's go ahead and take a look here at the code that I put together to do this. Now, I will say two quick shout outs. One, this code is assembled by a gentleman whose name I will not attempt to pronounce because it's Hungarian or something. But basically, this is his website. Engine Designs. He called it Retro Assembler. He just released version 1.2 recently, right after this, right before this video. This assembler is super easy, straightforward to use. He's even wrote a plugin or language encoding effectively down here for Retro Assembler. So you can use this with Notepad++ to write your assembly language programs, then tie it in with this plugin here with NPP exec and like auto compile just by hitting Shift F6. It's pretty nice. It's not a full IDE, but for what I'm doing, I don't need a specialized IDE. I just need something that I can put code in, read it, and click a button and get an output binary file. And that's exactly what this does. So it's really cool. The code here is inspired, nearly directly plagiarized, but changed a little bit from this guy here. I think his name is Dirk Grappendorf or something like that. He built the 6502 computer, his own single board computer. And it's basically the same idea that he's using a very simple program that connects over a terminal to just send that data out. This is a little trick to tell the assembler to start at the beginning, and then I start my code at E000, which is the beginning of the ROM code. First thing we do is we init the ACIA with these bits here to tell it, hey, this is how we are setting up the actual chip for communication. Then we do this, and we send it to the control register to say we're using this baud rate, this clock source, XYZ, all of that stuff. Then, we run through a loop. We sit here and we check to see if the buffer's empty. If it is, we keep checking until the buffer's empty. And this is what it does when it first turns on. If the buffer's not empty, then we grab a byte of the message, which I have down here. It just grabs a byte out, and we just spit it out. If it's not done, we grab it and we spit it out again and spit it out again and spit it out again, and then pretty much do it like that. When we're ready, we, index, jump back, and try again. Then after it has spit out the whole message, it sits into a wait mode. And it just goes and checks the ACIA and says, hey, you have a byte waiting for me? And if it does, then great. It's like going to go right up to here and spit that out again. But if it doesn't have a byte waiting for it, it just sits in a loop. Super tight loop checking the ACIA. Hey, give me a byte, give me a byte, give me a byte, give me a byte, give me a byte. If it doesn't have one, then, it doesn't do anything. Very simple output, simple hello world with a return character and zero null terminated string, zero terminated technically. Zero terminated string here that just tells at the end of the string, which, tells us the null terminated right here, branch if equal to 0. It just tells us, hey, we're done sending the message. And then I have this segment here that just sets the vectors. These are the standard 6502 vectors, E0, 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 which basically says no matter what happens, always come to the beginning of the ROM and start. We can change these values later to be somewhere else in ROM, or even potentially in RAM, or there's lots of different things that we can do later on with these vectors. That allow us to hook and change what reset is going to be. But again, way down the road. So yeah, that's pretty much all there is to the code and the machine. So let's go back over and take a look at the machine one last time. And we're going to look a little bit at some of the schematics. I have cleaned this guy up quite a bit, and let's refocus just to make sure we're down on that. Again, the oscillator and reset circuit are not any different. The 6502 layout, I have cleaned this up. I actually had some errors in the previous schematic. I hope nobody out there has built a machine based on the previous schematic, because there are errors on there that I wouldn't be surprised wouldn't burn up your 6502. So for any episode 3 and earlier, look at those schematics, recognize they're wrong, and don't use them. They're bad. But I went through and cleaned stuff up. So here we can actually see some of the details. We have our proper decoupling capacitor between 5 volts and ground. I have it on this. I really have it tied between these 2 pins here, but it's easier to show it on the schematic over there. Our ready pin, IRQ pin, and NMI pin are all pulled up to VCC with 3.3K resistors. And the same thing over here for the bus enable is pulled up to 3 volt, or pulled up via 3.3. The set overflow pin is also just pulled straight up to 5 volts. These are the standard recommendations for 65C02 processors. Same thing with like the vector pull here, and there's like the sync pin, the the ML, I don't remember what that pin is. These pins are just, they float. These are just the standard recommendations. So that's all nice and clean. You know, we've got our oscillator circuit has, and I'm going with the old school 6502 designations and not the 65C02 designations here because they were a little bit confusing and caused me some problems. Just basically because I don't understand what am I doing. But yeah, we have the phase 0, the master clock out comes into the phi 2 here, and phi 2 out comes out of here and is actually phase 2. This is actually phase 2. It's 0, 1, and 2. A lot of these are in sync but slightly offset, so you would figure, oh, it doesn't matter. Yes, it does matter which one of those you're using when you're referencing different chips in the machine. Very important. Don't screw it up or you end up having other weird issues. RAM and ROM over here. These are pretty straightforward. Address and data bus, no problem. Our pin 16 on both, again, tied to ground, just tied low. So we're only using basically the bottom half of each of those chips. Both have their decoupling capacitors here. On the ROM, because we don't want to be accidentally trying to write to this guy. Even though it's got software protection, you have to give it a certain byte sequence to be able to even program it, but we don't ever want that to float low, because that's with that little hash there means this is a negation. We don't want that to float low and accidentally try to program this, so I just tied that straight high, no problem. Then our chip select and output select are both pulled into the ROM select line. Basically, the reason for that is this. You know, I could encode those with different lines, but the way I see it is if this chip is enabled, because this is an output-only chip, that means it's going to be outputting data. If we're in the space of this ROM, this chip wants to ever talk to the bus, it's going to be outputting. So we just tie those both to output enable and be done with it. It's also a little extra insurance, like if there's something wacky with the chip for some asinine reason, who knows why, and like the output enable like doesn't matter to it or whatever, by tying those both, that will make doubly sure it's only ever going to be active when that's selected. The ROM encoding is, or the RAM encoding is a little bit different. The RAM the specific RAM chip that I'm using here has 2 chip enable pins. I'm not exactly sure what you would use that for. Probably for bank switching or something that effect, so you can switch in different chips at different points, different times for whatever reason. But in this case, I do not need that second chip enable line on this used, but it has to be tied. It has to be high in order for this chip to be enabled. So I just pull that high at all times. And then we have the chip enable, output enable, and write enable lines. You know, chip enable here just has to go low. That connects to my RAM cell, which is down here off of the address decoder. Output enable, again, also tied to RAM cell. In this case, because it's the easiest way to hook it up and make it work. I don't have to do any extra logic. I just tie them together and it works. That means that when the chip is enabled, its output is enabled. However, because of the way this chip works, this chip will only write to the bus when write enable is pulled low. When write enable is pulled low, it literally does not care what the value of this line is. It does not care. So if chip enable is pulled low and write enable is pulled low, that means, hey, I'm allowed to basically receive data from the bus and write it into memory. It does not care what the output enable is. It ignores it, so it just works. Address decoder. Here's, you know, the address decoder in a little bit more detail. Here's the primary address decoder, which is outputting our IO select line. This is the D, our E line and our F line. Of course, our E and F line are both the ROM chips, so those come together into the AND to make ROM cell. And that's really all that's doing. These upper line, or these lower lines, I'm not using for anything. I don't foresee using them for anything, but again, like I said, I could use them for some sort of bank switching magic down the road if I wanted to. Tie those into some other selection logic, put it in between here, so then I can like select different lines of the ROM or whatever, you know. This guy here is the IO decoder itself. It's got the 8 different outputs, so we can select 8 different sections of the IO memory space to pick devices. Right now, both of these go into an extra input of this NAND gate, because if we know our logic, two NANDs basically make a negate. Two NANDs together negate. So if I bring both of those values together into the two inputs of one NAND gate, what do I get out? I get out an invert. And that's exactly what that does. And that goes to the select line of my ACIA chip down here. Later on, when I select, say, a video chip or a sound chip or a 6522 for lots of input-output pins or whatever I want to do, I can connect those to these other pins and just address it like any other chip. Here's the serial port. Again, I went through over most of that. We've got our select line to select this chip specifically, and then the I/O select line, which is for the whole I/O area. That allows us, when we're in the right part of our memory space, that chip's selected. Reset goes to reset. Our TXD and RXD lines come over here to the max chip, and then our address and data lines. Read, write, phase, all that stuff needed to synchronize with the 65 CO2. Over here's the oscillator circuit. It's pretty straightforward. This is the suggested oscillator circuit that comes with the 65 C51. I put that in there because that was what I was originally wiring the board for. But then I ended up putting it in the 6551, and it works with that circuit. These are just like, noise suppression. It's like a noise suppression decoupling type capacitor there. And the 1 megohm helps remove, ringing or inductance. It provides bias. I'm a very electronics noob, so I'm not sure what exactly those, the purpose of those are, but it works. So, the 6551, the standard 6551 says just shove a crystal across it. It'll work. But, whatever. It's in there now. It's working, so I'm leaving it alone. Again, because this is direct pin compatible with the 6551 or the 65C51, the only thing that's truly incompatible is how you use your software to interface with it. I went ahead and decided to design it this way. If somebody down the road, if they're having problems getting an actual 6551 or one of the non-Western Design Center 65C51s, they can put one of those in there, and they just have to modify the ROM code a little bit to create a little polling loop to wait to send bytes out, so you don't have to worry about that transmit bit stuck issue. And this is pretty straightforward. This is that max 233. Basically, the pins that need to be open are open. The ones that the datasheet says need to be crossed are crossed over here. Our data comes in and goes out, or it comes in from this side and goes out to the chip. And that's really all there is to it. Lots of decoupling capacitors, simple 100 nanofarad or 0.01 microfarads, however you want to read that out. Smattered all over the place just to make the bus stable. Pretty straightforward and easy. That all said, JCM-1 could be even theoretically done right now. This is technically a computer. It has full proper input and output. And all I would have to do is put the right program in it, and over my serial port, I could do pretty much anything with the computer I wanted to. But it's lacking a lot of extra features we might want in an 8-bit computer, like, more input-output than just the serial port. What if we want to run motors or actuators, blink lights, make sound, send video out to a monitor, do more fancy things? Well, we need to keep adding stuff to it to do that. So that's where we're going to go next. I'm not exactly sure what I'm going to put in here next. I'm probably going to go for the 6522 chip, the generic I/O chip, the generic 65 series I/O chip, because that's going to give me a lot of flexibility. That thing can address, a single 6522 can control tens, if not hundreds of different devices if you use its output pins intelligently. It can do an insane amount of work and make basically single chip glue logic for just about any input output you want out of the machine. So I might do that next. I don't know. I might want it to do something fancy and decide to just throw a sound generator in there to make it make noise. I haven't decided yet, but as I said at the beginning of this project, I'm just letting the project kind of talk to me, just to whisper in my ear, go with my whim, and tell me what we want it to do. Well, that's all for JCM-1 today. I hope you enjoyed this little trip with me. If you have any questions, leave them in the comments below. If I did something wrong, yell at me in the comments below. I am still learning, but whatever. I also have Facebook and Instagram if you want to try to reach out to me on those media, especially the 6502 group or the Apple II enthusiast groups on Instagram. I'm on those. I read those daily. So if you're wanting to ask me something, jump on there and say, "Hey Joe, hey, I had a question about XYZ or whatever," and put it on there. Links in the description to everything I talked about, and that's it. That's all for today's video. I really hope you enjoyed it. If you did, let me know. Watch a couple other videos while you're here, and remember, 8 bits are all you need.